And I'm delighted to introduce to you this morning our leading speaker, Dr. Andrew Pinsent, who is the Research Director of the Ian Ramsay Centre for Science and Religion at Oxford University, a Research Fellow of Harris Manchester College, and a member of the Faculty of Theology and Religion at Oxford. With multiple degrees in physics, theology and philosophy, including a PhD from Oxford in particle physics and a PhD from St. Louis in philosophy, it's fair to assume that Dr. Pinsent has drawn upon many resources in forming his views on the subject of the metaphysics of many body physics. Dr. Andrew Pinsent.
I'd like to begin by thanking William and his colleagues for organising these conferences. In fact, I've been recommending to people to go online and look at the recordings of last year's Physics and Philosophy Conference in St Andrews, because there were such brilliant introductions, particularly to quantum mechanics, and some of the best introductions that I've ever come across. So thank you for taking this initiative. And by the way, if you don't already know this, William Simpson is now Dr. William Simpson. Would you like to please join me in congratulating? Well, my subject for this morning is the metaphysics of many body systems. And as William said, I used to be a physicist many years ago. And when physics is actually portrayed by our popular media, it all seems rather Olympian. In fact, my experience of experimental particle physics was testing 10,000 gas connectors supplied by the cheapest supplier, and adjusting a few lines in a million lines of Depth-Ware Fortran. So it's a lot of very hard, detailed work in physics. I worked on the Delphi experiment, and we were looking for the Higgs at the LEP. I didn't find it, unfortunately, but it was certainly a very useful experience for me. Very grateful for that. Now, what I tend to find, when we talk about the philosophy of physics, the frontiers stimulated by contemporary physics are often held to be the very small, the very large, the very fast, or some combination of all of the above. And I suggest what is less widely appreciated is the extent to which our physics, and also many of our most commonly held philosophical commitments, have been shaped by the behaviour of a single kind of system with unusual metaphysical characteristics, the two-body, idealised Newtonian system. So obviously something like a single planet and the sun orbiting a common centre of mass. And if you want to give as an example for this, Professor James Ladyman, who spoke at last year's conference, wrote quite an influential book, Everything Must Go. And he talked about that it's really a call to philosophers to take more interest in contemporary developments in science. But there's very, very little talk about many-body systems. So even people who spend a lot of their lives thinking about these issues don't seem to pay too much attention to the way that we look at the world through the lens of the two-body system. Now, of course, there's a possible objection to this. We do in fact study many-body systems, and for as a definition, by many I mean more than two. So more than two. We study many-body systems in physics, but we study these systems as aggregates or as perturbed approximations of two-body systems. So in kinetic theory of gases, we're treating a whole load of atoms bashing into one another, or with perturbed approximations of two-body systems, we really start with the two-body system, and then we just nudge it a little bit, which is actually how Neptune was discovered, by nudges to the orbits of the other planets. And there's a very good reason for this. These two-body systems are the only systems we can integrate over time analytically. So there's something which works very well. For the solar system, it works very well for a lot of the things we're interested in. Atomic physics, what we can do is we can treat the electrons initially as separate from one another and then just tweak them slightly. It gets more difficult for nuclear physics and almost impossible for quark-gluon physics. Now, for this presentation, my concern is not with the limits of two-body approximations for physics, but the implications of metaphysics. If we look at the world with blue-coloured glasses, we see only blue objects, which is fine as long as you remember you're wearing special glasses. The problem is, if you get to the point where you think you forget about the glasses and you assume that's all there is. What are the implications for perceiving the world by means of the techniques of physics that reduce everything to two-body systems? Now, the claim might be made, in fact has been made, the issue is simply computational power. There's no real mystery. Okay, we can't integrate analytically the more complex cases. We have to use all these clever techniques, approximations, and so on. But in this presentation, I shall oppose the claim that there's no mystery and argue that the Newtonian two-body filter has in fact warped and seriously restricted our understanding of the physical world. It's a loss of matter and time in Newton's strange world. What is matter? Whatever is material, concrete, tangible to our senses, especially touch, is frequently regarded as setting the standard for what is real and most reliably known. For this reason, to give one famous example in the Christian tradition, it is not surprising that the test Jesus offers in the Gospels of the truth of the resurrection involve touch. As is well known, material things and their acquisition have also become a measure of high or even ultimate value in many societies, especially in the last century. So Solzhenitsyn, in his famous Harvard commencement address, was lamenting this turn towards materialism, warning that it's taking over. So he contrasts the Middle Ages. He describes it being over-spiritual. We recoiled from that, became excessively, incommensurably material. The humanistic way of thinking, which proclaimed itself our guide, did not admit the existence of intrinsic evil in man, nor did it see any task higher than the attainment of happiness on earth. It started modern Western civilization on the dangerous trend of worshipping man and his material needs. Everything beyond physical well-being and accumulation of material goods, all other human requirements and characteristics of a subtle and higher nature were left outside the area of attention of state and social systems, as if human life did not have any higher meaning. See, this came home to me on a very personal way. I was visiting a church in a poor part of Barbados, and I remember asking the priest there, what do you need? And having a very materialistic concept of poverty, I assumed he said, would say something like clothing or food. What he said, what we actually need is books. And it really struck me very strongly. Even the way we look at poverty today is constrained very strongly by an emphasis on materialism. And even those who are in great material need quickly actually need other things besides material goods. It's an insult to them to think otherwise. So reduction to the material. The shift in culture and ethics towards reduction towards the importance of matter as a first cause of human value can also be seen in the role of matter as a first cause in some philosophies. These are the spiritual heirs of Thales. Thales was the first person to come up with a grand unified theory of the world. He said everything's made of water, which is not a foolish thing to come up with initially. Now such philosophers are generally called materialist or physicalist. The relationship between these terms being a matter of ongoing debate. The general thesis is that everything is material or physical, or, as contemporary philosophers sometimes put it, everything supervenes on or is necessitated by the material or physical. So you think we have a good idea what matter is, if matter is so important to us. But what is matter? Well, here's a typical dictionary working definition. Physical substance in general as distinct from mind and spirit, or in physics, that which occupies space and possesses rest mass, especially as distinct from energy. And note here the use of the term matter as distinct from something else. It's a kind of trouser word. You need to know one leg of the trouser by the other, so to speak. It's something that was contrasted with something else. Matter contrasted with form. Are these sequences the same or different? GCTA, GTCA. I mean, are they the same or different? They're different and yet the same. They're the same in one sense and different in another. It's a simple example, but here we get the beginnings of the idea of matter and form, what a thing is made of and how it's structured or ordered or assembled. And so quite early on in Greek philosophy, a distinction began to be made between matter and form. You might think, by the way, this is a very simple example, already you can get quite a lot out of this. I remember when I was at school, a common line I heard in the classroom was, we are 85% water or something like that, as if we're nothing but water. So as if what we're made of really is a measure of our value. Or, does anyone know Aquinas' definition of the soul? Just curious. The form of the body, yes. So just out of matter and form, we're already beginning to get a toolkit that can be used for quite sophisticated issues. And incidentally, as a priest, I quite often see the difference between a person who's close to death and a dead body. It's very interesting, the change from the loss of form. So Newtonian physics and matter. Now it might seem that modern physics is intrinsically linked to a world that prioritises matter, but the role of matter in physics as developed from Newton is more paradoxical than it might seem. So how does the Newtonian analysis of the orbit of one planet, one material object around the Sun, another material object? Well, the basic simplification is to treat both objects as mutually attracting point masses. The matter, the stuff, fades out of consideration. And nothing matters about the matter except insofar as it contributes to a resistance to acceleration. Everything measured, calculated and predicted is actually formal. And this is particularly important. Future states are analytically reducible to present states, and time becomes like space. This initial will pick up later in the day, but time is essentially frozen, becomes space-like in this way of looking at the world. And is matter, well, maybe matter is extended stuff. If everything is reducible to matter, what do we find when we study what matter is, especially what matter is made of? Take Berkeley's principles of human knowledge. Matter is an inert, senseless substance in which extension, figure, and motion do actually subsist. But as we look closer and closer, it seems to dissolve as chimera upon investigation. Every piece of matter reveals itself either to be composite or elementary, and what is elementary behaves as if it's point-like, albeit with a surrounding zone of attraction or repulsion, a field to other elementary particles. This is a bit of forgotten history of the philosophy of science. This is a page from a book written in 1763 by Roger Joseph Boscovich, largely forgotten in Anglo-Saxon countries. Looks remarkably like a modern physics textbook. The force curve, the idea of the attraction of two particles is already present here, and has attracted a lot of attention from later philosophers like Priestley, Davy, and Michael Faraday. Exotic states of matter. The notion of matter being any kind of extended stuff is also called into question by some of its more exotic states. We predict, for example, under extreme conditions, forces of repulsion that keep matter extended can collapse. Atomic orbits can collapse to form what are essentially giant nuclei, several miles across, which are neutron stars. And nuclear repulsive forces can also ultimately be overcome by gravity to form black holes. We're not sure what happens then. The elementary particles that seem most solid can also be transformed into the more ethereal objects of the physical world, such as photons or neutrinos. So this stuff that looks so solid to our senses from everyday life, is a heck of a lot more mysterious as we look closer and closer. And of course, the very idea, if you said 150 years ago, our present theory of the origin of the universe is exploded out of a point, they would have thought you were crazy. But this is how we now imagine it. Imagine the universe being almost infinitely compact initially. And we imagine states of matter in which they can almost, which the matter can be compressed practically infinitely. So matter, and especially what is measured by physics, has secured a position of a kind of first principle of being, of knowing and value in our society, while immaterial and formal things, ideas, relations, possibly souls, are held to be reducible to or supervene on material or physical things. Paradoxically, however, it has become steadily less clear what matter is, or what role it plays in physics other than exemplifying form. The notion of matter as extended stuff turns out to be peculiarly illusory when asked where ultimately is the extension. Physics in the tradition of Newton seems to have little or no use for matter, except insofar as it contributes in some aggregate way to sets of formal properties. So we've got the paradoxical state of materialism today. That's really formalism. The paradox is that the materialist age is in fact dominated by formalism, especially mathematical formalism. And it's not uncommon to find a claim that reality reduces to number. A particularly prominent recent exponent of this is Max Tegmark, who's done also a lot of work on multiverses, with his mathematical universe hypothesis. Of course, this is very strange to a philosopher because numbers are themselves ontologically dependent. There's always an implicit of, number of, at least in traditional philosophy. Now, of course, we can argue about this, but the mind abstracts numbers, and then we can then think about them separate from matter. But there's always an implicit relation to something, some standard which is not itself mathematical. Instead, if you want to challenge that, you might think that something simple like 2 + 2 make 4 is incontrovertible. But if you go to a supermarket and you buy, say, 2 cans of beans and another 2 cans of beans, you might expect to pay not the equivalent of 4 cans of separate beans, but 3.8. Even the basic situation of supermarkets, we expect numbers to behave differently than we do necessarily always in the classroom. So, mystery of chaos. Now, Newtonian physics radically changed our worldview, namely the complex motion of each planet to be explained in terms of a few simple mathematical laws. But Newton's failures are less widely known, however. As I say, I went all the way through to a PhD in physics without realising this. He tried to apply his techniques to a more complex case, the Sun, Moon and Earth, and found he could not integrate the equations. And since the 19th century, it's now known that such integrations cannot usually be done analytically. There are special cases. Now, of course, in the case of the solar system, this failure is masked because, to a very good approximation, the whole system is dominated by one major body, the Sun, and so the solar system can be modelled fairly well as a simple aggregation or sum of two-body systems. And then we can use perturbation techniques to add the planet-to-planet interactions. As I mentioned earlier, we can do something similar for atomic physics. Again, the nucleus dominates, but it becomes steadily more difficult as we get to nuclear physics and then quark-gluon physics. In fact, brute force mathematical approximations using supercomputers are the only known way to try to calculate the behavior of the whole from the sum of the parts. Now, at least part of what made Newton's physics so attractive was, of course, the ability to make mathematical predictions of future states from present states of systems, linking past, present, and future together analytically. It's hard to overestimate the importance of this development for our intellectual tradition. A good deal of the history of modern philosophy has been shaped by all these developments in physics, either implicitly or explicitly. Now, since the 1960s, and the pioneering work of Edward Lorenz, initially in the area of weather forecasting, it became apparent that some systems are radically unpredictable. Small change in initial conditions, like rounding errors in a computer program, produces a change in outcome that diverges exponentially from the present behavior of the system with the simulated time of the presentation. All this is fairly familiar, but the philosophical implications are not always drawn so clearly. the system described by the equations isolated by Lorentz has another peculiar property. So classical systems, like a pendulum, have attractors in a phase space that describes the state of the system. In the case of a pendulum, in a space defined by position and momentum, the state will spiral towards a central point as the pendulum dissipates energy. That's a dissipative system. The simulated behavior of the system described by the Lorentz equations also has a final state, but this is not due to the dissipation of energy. Repeated numerical integration from any starting point in a three-dimensional phase space produces a trajectory that moves towards and then remains in the vicinity of two interconnected regions, a characteristic shape known as Lorentz butterfly. Is this familiar to most of you? Lorentz chaos? Is this new to some of you? Is it new to some of you? Yes, okay, I'm adding value, good. So there we are, the behavior of the attractor of a classical system, that's all fairly familiar, hopefully, with A-level physics or so. With the Lorentz system, wherever you start in the phase space, the trajectory always ends up in the vicinity, in the butterfly wing vicinity of this attractor. It's called a strange attractor. I hope to set up a nice mathematical simulation. If you go onto YouTube, you can find a list of nice simulations of the Lorentz system. And it's done one here. Whatever the starting point, the point always ends up in the general vicinity of this shape. There. And a lot of people then have looked at this and said there's parallels in nature, things like the red spot on Jupiter and so on, or possibly. So, divergence of strange attractors. The Lorentz system, and many others like it, exhibit two remarkable behaviors. Uncertainties in initial positions of points inflate exponentially, and all points end up in the general vicinity of the strange attractor, the Lorentz butterfly. There's a very good book on this, Peter Smith, Explaining Chaos, published in 1998. And he gave an example of just how powerful the exponential effect is. So if you have two computers that have the same starting points, everything's the same about two systems, two Lorentz systems, same starting points, and within a small error difference of delta x. And suppose also that both computers always calculate that the point is on the same wing of the Lorentz butterfly after time t, but then diverge. Now, how much should the difference delta x be reduced to ensure that both computers produce the same result 100 times later after 100 t? And the answer is 40 orders of magnitude, roughly equivalent to shrinking the entire distance from Earth to the edge of the observable universe down to the size of a proton. Which way of underlying all predictive power. For all practical purposes, there's a breakdown of all predictive powers in these systems. Hence, of course, they've been given the name chaos. They've been given the term chaos due to the lack of predictability. But this specification is not wholly satisfactory, since the same characteristic is true actually of some ordinary classical systems. From the very start of the study of this field, what's been very odd about it is it's been misnamed. Chaos is not enough really to distinguish these special cases from some kinds of ordinary classical systems. And, more importantly, chaos actually fails to capture what is arguably the most intriguing aspect of these systems, which is that they're not chaotic. Any starting point of a trajectory in the phase space will end up somewhere in the vicinity of the strange attractor. So that the position of a particular point rapidly loses all predictability, all points will end up in the general vicinity of the attractor. So the very name has captured or partly captured one characteristic of these systems, but completely fails to capture the other. So in fact, in the early days, when these phenomena were being discussed or reported in the press, there were articles like, the solar system is now chaotic, it's all going to fall to pieces. Well, it's not quite that, it's not really saying that. There's this order, but it's not the kind of order that we're normally used to seeing. So matter and chaotic systems. When analysed in Newtonian terms, a point moving in a phase space, this is how we've been doing, this is how we work in dynamics for centuries. When analysed in Newtonian terms as a point moving in a phase space, the most apparent characteristic of a chaotic system is the loss of ability to predict precisely the position. So if we look at it the same, we look at chaotic systems the same way as we look at Newtonian systems, what we see, the most obvious characteristic that we see, is loss of predictability. And of course, the choice of model is not accidental, it's part of the Newtonian tradition. The tradition represents everything important about the dynamics of an extended moving body, such as a molecule or planet in orbit, in terms of a single point, a mathematical abstraction called the centre of mass. Now, I was puzzling, I thought there was something wrong with this. I'm grateful for Professor Raymond Tallis for a short article he wrote in Philosophy Now on points. Professor Tallis was attacking the notion of points. I thought, yes. So someone's thinking along the same lines here. There's something odd about points. Points have to borrow space from other things, such as dots or ink marks, which are not dimensionless. In order to represent them visibly on paper or on computer screens. So going back to these pictures, of course you don't see a point. You see there are actually marks on the computer screen, and the point which is actually moving is allowed to trace and leave its pattern behind on the screen. So actually you're not really seeing a point, you're seeing the traces of an orbit. So consider what happens. Rather than think of the chaotic systems in terms of one point to another point, think of beginning with some extended object, which itself has order, itself has information. I'll give you some examples of extended objects here, tetrahedra or star shapes, or random shapes, completely randomized sets of points. And whatever you start with, you end up with something which looks like the Lorentz orbit. With these examples, what is clear is that any extended object demarcated by a set of points of the phase space, configured in any form whatsoever, will be transformed into the wings of the Lorentz attractor. And notice that in some cases, you get an increase of order, not a decrease of order. So we're not breaking things down. So you can start with random points, you end up with a more ordered state than you start with. Consider from the perspective of extended objects, it is clear that the initial information, the form of the initial shape, is removed systematically and replaced with new information, the form of the strange attractor. The claim that all predictive power is lost is incorrect, however, since the attractor emerges no matter how many times the process is repeated and whatever the initial structure. So, what, if anything, is the principle of continuity between the initial and the final states of the system? Well, I would suggest it's not true that there's no causal connection between past and future. Every point within or on the boundary of the initial extended object will eventually map onto some point in the general vicinity of the attractor. And although the points are dimensionless, if the standard heuristic is adopted of labeling a subset of initial points within the initial object with tiny identical dots and ink marks, which are not quite dimensionless, the overall volume of dots or ink used will be conserved between the initial and final states. So if we have half as many points at the beginning, we'll have half as many at the end, double number at the beginning, double number at the end. And the strange attractor will continue to be visible as long as the marks are sufficient to demarcate the general trajectories of the orbits, the trail on computer screens in simulations. The shape is only rendered invisible in the limiting Newtonian case when the system is modelled as a single point in the phase space at the start of the process and a single point without a visible trail at future times. This conservation suggests a some principal continuity between the initial and the final states of the system. But the continuity has a peculiar characteristic, that an answer cannot be given to the question of what this principle is, if an answer is required in the customary manner of formal mathematical objects, such as a numerical value, a position in space, or some determinate geometric form. I suggest, therefore, this principle is properly called matter. I suggest that unlike the Newtonian system, for which matter does not really matter in connecting initial and final states, in so-called chaotic systems, matter does matter, and indeed it's the only principal continuity between the initial and the final states. So, is matter just extension, which one of the things we looked at earlier doesn't seem satisfactory? Well, if we think of matter as a volume bounded by some limit, such as the limit and the volume it encloses are conceptually separated, that's one way of thinking about matter. But in the case of a well-defined geometric object, or a well-defined object translated through space in a Newtonian manner, all that is required to answer the question of what the object is can be obtained from the formal definition of the object. So a cube in a mathematical space can be defined simply as a symmetrical three-dimensional shape contained by 6 equal squares, and nothing more needs to be said. The matter is superfluous except to exemplify form. The need to distinguish a further principle, a further philosophical principle, only arises when the initial form is eliminated and replaced with a new form, but there's some underlying continuity which is not itself form. This continuity is indeed imagined and thought of as a volume of space, but not a particular bounded volume, since all such particularity is of its nature formal. And such a principle appears to correspond closely to how Aristotle described highly matter, namely as that is which in itself neither a particular thing, nor a certain quantity, nor assigned to any other of the categories by which being is determined, but which is known by means of the continuity through generation and corruption of particular determinate beings. And this he's getting very much out of biology, out of the metaphysical biology. So living things, what you've got here is a transformation of matter from certain kinds of forms into the form of the living thing. And from this he gets a lot of his principles of his philosophy. You get the idea of substance and accident. You get the idea of change from initial forms to a living plant with matter as a principle of continuity. You get the idea of final causes, teleological causes, ordering towards an end. And from final causes, we get the understanding also of good and evil. And this is not, the implications are not trivial. If you get rid of metaphysics founded on biological principles, there are actually only 3 sources of morality: one's own will, the state, or God. There's nothing else left. Incidentally, going back to this, it's interesting. We tend to think that living things must reduce to mechanical systems. I want to show towards the end, I think it's the other way around. We actually see some mechanical systems that are more like living systems. So objection, is there a genuine need for some non-formal principle of continuity? So some objections to this suggestion we need matter, we're seeing something radically new. Can the strange attraction of the Lorentz system be formally reduced, at least in principle, to an initial state of the system? If so, then we can do without matter as a principle of continuity. And there might be reasons for thinking this. The information is severely scrambled in the attractor, but possibly still available in principle. Or the very fact we can generate a computer representation. A computer is a formal machine. So doesn't this invalidate the case that we have something metaphysically new? Well, as a first response to this, it's worth noting the initial state doesn't seem to matter. Whatever the form, wherever the information comes from is not from the initial state, the initial configuration of the points. Whatever the distribution of points to begin with, delineating any shape whatsoever or no shape at all, they all end up looking the same, distributed around the strange attractor. Whatever the form of the strange attractor comes from, wherever the form comes from, it doesn't seem to come from the initial configuration of matter, which is quickly broken down in simulations. But it's also worth recalling what computers actually do in simulating chaotic systems. Computers don't actually solve the equations over any time interval, no matter how small. All they do is plot an approximate trajectory through a series of stepwise iterations, using an approximation of the equations that is amenable to calculation. There's always an etiological gap, causal gap. No matter how small the time slice, the state of the system, the actual system, properly worked out system, cannot be reduced by some finite analytical equation to the state of the previous time. And moreover, the final shape, the strange attractor, is not even formally describable, since it is a fractal. The computer reveals the general shape, but it can never wholly compute it from the initial form. We see the shapes there, but the computer never formally describes it. In fact, that's actually formally impossible. Now, some of this was seen in the early days of chaos, but the full implications never seem to be quite drawn out. This is a wonderful article on chaos in Scientific American by PhysPhil, Farmer, Packard and Shaw. This is just when interest was really getting underway. The stretching and folding operation of a chaotic attractor systematically removes the initial information and replaces it with new information. Chaotic attractors act as a kind of pump, bringing microscopic fluctuations up to macroscopic expression. In this light, it is clear that no exact solution, no shortcut to tell the future can exist. After a brief time interval, the uncertainty specified by the initial measurement covers the entire attractor and all predictive power is lost. There's no causal connection between past and future. Now, in this article, the chaotic attractor was described as systematically removing initial information, replacing it with new information. But the claim that all predictive power is lost is incorrect. The attractor infallibly emerges, no matter how many times the process is repeated, and whatever the initial structure. Indeed, the attractor can increase, not decrease, order. And it's not true that there's no causal connection between past and future, although it's impossible to see it if the system is analysed in standard Newtonian terms as a monadic point moving through space. The cause that connects initial and final states is not formal, but material. Moreover, the fact that the system tends towards a final state and the irreducibility of the final state to the initial state also means that the final state of the system acts as an Aristotelian end or final cause. Let's first start to think about these issues. I was really quite struck. When I was at school studying physics, Aristotle was occasionally mentioned as a sort of foil, a kind of foolish figure from ancient Greece who got teleology and got it wrong, and we've done better since then. And suddenly, you see teleological type behaviour emerging on the computer screen in modern dynamics. It's quite extraordinary. This is more subtle, but I suggest the chaotic system is probably characterised not merely as teleonomical, as a kind of backdoor reintroduction of a bit of teleology in biology, teleonomy. But I think this is a genuine teleological system, the operation of which can be likened to a neo-Aristotelian pump or engine for breaking down and systematically replacing any initial information by a final form. The only principal continuity between the initial and final form is a material one, hence matter matters. Conclusions and implications. Chaotic systems have usually been studied and even been misnamed from a perspective conditioned by Newtonian thinking, the trajectories of a point mass in an absolute space. I mentioned at the beginning, if you look at the world through blue glasses, everything looks like a blue object. If we look at the world through this perspective, chaotic systems puzzle us. From this perspective, the dominant characteristic is a rapid erosion of reliable prediction. This behaviour gave such systems the name chaotic, even though they actually change one kind of order, or even disorder, into ordered forms. If the study of these systems is considered in terms of changes to extended objects, then there is an irreducible final cause, the strange attractor, and a principal continuity between initial and final states. The principle, however, is a material one in an Aristotelian sense, not a formal one. How else does matter matter? As has often been remarked, chaotic systems do not undermine determinism directly. Although the fact that the whole is not the sum of the parts in these models raises the possibility that natural systems may also exhibit causal behaviour that is more than the sum of their parts. Such systems, however, do break the Newtonian symmetry of past and future, reintroducing the arrow of time. More subtly, these neo-Aristotelian systems can also be said to unfreeze time. That was a challenge raised by Lisa Owen in one of the book called The Trouble with Physics. There's only one graph in it, and it's a graph of t and x, space and time. And he refers after it to saying, maybe this is the smoking gun. Maybe this is where we're going wrong. We need to find a way of unfreezing time to represent time without turning it into space. Maybe this is one way of doing it. A future state is not really a mathematical function of a present state, a characteristic of Newtonian physics that has a tendency to turn time into space. How else does matter matter? An influential pattern of thought in philosophy, in the humanities generally, and the broader culture is a belief expressed by a litany, which you often hear it is expressed as a litany, that biology is reducible to chemistry, and chemistry is reducible to physics, with physics ultimately reducible to some variant of Newtonian formalism. The older, more organic Aristotelian thinking has been held to supervene on this more mechanistic foundation, and this has vastly shaped the Western imagination for centuries. The value of chaotic systems in dynamics is that they have been simple enough to study exhaustively and challenge this assumption. Although these models are also idealizations of nature, they show that the Newtonian idealizations are no longer the only story. Final causes and matter matter, and this fact should inform our philosophy and our theology. And the final theological coda. Since God is held to be immaterial in his divine nature, and because of the seemingly divine-like attributes of ideas, forms, and mathematics, there's been a constant pull in many intellectual and spiritual traditions to prioritize form and to regard matter as intrinsically unimportant or even suspect. And we actually, every now and again, in Christianity, there are waves like iconoclasm, where we smash images and so on. And this is almost like a rejection of matter. If, however, matter matters in dynamics to enable substantial change from initial to final forms, perhaps it is time to reassess the importance of matter even in matters of the spirit. We cultivate changes to the soul, the form of the body, by means of sanctified and sanctifying matter. The perfection of the soul may be the end, but as the early Christian writer Tertullian remarked, the flesh is the hinge of salvation. Thank you very much.
Thank you very much. A very enriching talk. I'm sure there will be some questions.
Thank you very much for the talk. I've always been interested by the three-body problem, but I'm just curious. This probably has no importance for practicing scientists at all, but purely philosophically, does this mean that even Laplace's demon would not be able to tell the future of these things, or would we just say that demon doesn't exist, can never exist, therefore don't think about it?
Well, Laplace's demon could never predict the future using purely formal methods.
Okay.
And that's the whole point. The future, since the time of Newton, what's given is physics, in many ways, extraordinary power, its ability to formally reduce the future to the present, and ontologically then they all look the same. And I think what these systems show is that this is not the case, and with a formal reduction that cannot be carried out, you need matter as well. Incidentally, on the three-body problem, if you haven't seen it, there's a wonderful documentary on, I think it's on BBC 4, on the approximate solving of the three-body problem for the exploration of the solar system. I think it was called The Final Frontier or something, about the Voyager missions, because they had to solve, they had to get good approximate solutions to the three-body problem to launch the Voyager mission. So it's extraordinary drama how that was done.
Thanks, that was very interesting. I was particularly intrigued by the thought that matter is the principle of continuity, and I just really wanted to get a bit clear about what that amounted to. And my understanding is that there's something there that needs explaining that can't be explained unless we have a principle of continuity, and then matter is going to be what takes that role. Can you say again, what is it that needs explaining that forces us to bring in matter?
Well, we need the initial and final states of one of these systems are connected in some way, and that's clear. But if it's not, but it can't be formal, so by a process of elimination, it has something else which we can call matter, and which corresponds to what some of the ancient Greek philosophers would have called matter, which is something we only know through substantial change. So, in a world of strict geometry, of just geometry frozen in time, as it were, you don't really need matter. Matter at this point, form is at that point abstracted from matter. It may be there in the models it's given us to imagine what a tetrahedron is like or whatever, but in the world of mathematical equations and geometric construct, we don't need the matter. But we do in the physical world. And we do now in some of these simulations of things in the physical world. But it's the name we give to that thing which connects the present and the future, but which is not formal. Basically, so again, it's a process of elimination, but we know it mainly through a heuristic argument, which I just gave there. That there's some kind of continuity of. You can call it volume, though volumes are very misleading because if it's a specific volume, it becomes formally described, which is we'll try to get rid of that as well. But there's some stuff is continuous, if you like, between the initial and final form. That's what we call the matter. In biology, of course, it's commonplace. I mean, living things transform matter all the time into their own form. But what I find striking is that for a long time we've been told that this world of living things ultimately reduces down to mechanism. What I find so remarkable is that some very simple mechanisms look much more like what we see in the world of living things, metaphysically.
Is the stock market a chaotic system? Is Ukraine a chaotic system? Or are they not systems at all?
Well, it's. I guess if you wear, I mentioned earlier, if you wear blue glasses, you see only blue objects. If you wear red glasses, you see red objects. I imagine you can perhaps overdo the chaotic thing a bit, looking at the world. But insofar as we get patterns of order emerging from initial disorder, quite often we can trace that back to something we would call a chaotic system. Particularly if these patterns are repeatable and there's some kind of regularity in the order produced. And weather systems obviously examples of these.
That question brings me something else which you didn't really touch on, is complex systems and complexity. So you kind of mentioned that there's non-chaotic systems, where chaos has a very clear definition, that nonetheless display impossible to predict only apply to complex systems, or does it also apply to chaotic, to complex systems as well as chaotic systems? So they don't have strange attractors there, for example, but nonetheless, like nebulous spots, for example, there's plenty of examples in biology.
Right. Yes, I don't quite know what definition you're using of complex systems here. The kind of systems I'm most interested in are the ones with the strange attractors, of course, because they exhibit teleology, some kind of continuity principle which isn't formal. If there are broader systems which you can call complex, I'm not an expert in those, and there may be a lot of other kinds of metaphysics, I don't know.
I want to ask about the idea that these systems exhibit genuine teleology. So I guess teleology is a matter of having a purpose or a function. I see you're suggesting that you're going to object to that. At least that's one standard conception. And I don't see anything like that here. I don't see any possibility of malfunction, for example. So could you say a bit more about how you're thinking teleology, if not in that kind of usual way?
Right. This whole area has been incredibly muddied. Immediately, if the term teleology is used, people immediately think purpose. And part of the problem is that because we've had two main metaphors for how we've looked at the world since the early Greeks, the organism and the machine. And when we switched to the machine metaphor, particularly after Newton, the only way we could think of teleology was in terms of purpose. And so the name has been slightly sort of, the whole arena has been mucked up. But you can have end-directed behavior without purpose. And even, we're creeping back towards this idea, even in other kinds of systems. So, even something similar like the thermostat in this room with feedback effects, as soon as you get feedback, you've got the possibility of some kind of end-directed action. Those systems are normally called teleonomical, because there's some kind of pre-programmed, there is actually a form at the beginning which determines the end. Chaotic systems, as I described it here, with the strange attractors, I would say are probably teleological, not just teleonomical, because the form is not there at the beginning. But it's not true to say that the end is a mysterious pull from the future either. It's the action of the equations on matter which produces the final form. Interestingly, things like snowflakes are another example. You've got, and there are many others in the natural world. We get to kind of spontaneous order, but it's wrong to then immediately say that's purpose. Purpose is, of course, teleological, but teleology is a broader term than that.
Thank you, Andrew, for that inspiring rehabilitation of Aristotle. Could I ask you about another muddy term that gets used an awful lot in the science theology conversation, namely emergence, and how this relates to emergence is used in all sorts of ways, often not specified very clearly. How do you see what you've been talking about relating to that muddy term?
Well, it's we've been creeping back towards a different view of the world in a slightly sort of guilty way. So if we can't use the word teleology, emergence has been one of the things we've used as a kind of substitute, I think. Again, the language has been, the water has been muddied for the problem I mentioned earlier, which is that in a mechanistic universe, the only kind of purpose you can think of is a purpose of intellect and will. And therefore, teleology became discredited. Then all this stuff came along, which looks end-directed. We actually almost had to invent new names, like chaos or emergence. Emergence is one way of, emergence captures some of the same sorts of things. But again, emergence is a term which has many different definitions, because the best thing you say is overlaps with what we're talking about here. It's like I think of Ernst Mayer's work on He doesn't use teleology, he uses teleonomy. So that's another example of people getting back towards the idea of a respectable end-directed action, because end-directed action is perceived as being somehow not respectable, even today.
I was struck by you emphasising the reintroduction of an arrow of time. So if you've got that, then chaotic systems are strictly in equivalence with Newtonian systems, which are reversible.
Yes.
On the other hand, often chaotic systems are discussed in terms of as a special case of classical systems, the ones that are not regular. So I think when you talk about different idealizations, each of which should be taken at face value without privileging maybe the Newtonian one, you were emphasizing a different perspective, not chaotic systems are special classical systems with fun behavior. Could you just clarify that point?
Yes. Thank you for mentioning the Arrow of Time again. That was actually a book on this quite early on in days of chaotic systems, with a title something like The Arrow of Time, I don't know the precise title. So you can add chaotic systems to these other kinds of systems that have been a bit odd from the Newtonian point of view. Entropy, quite early on, was recognised as being odd because it seems to have an arrow of time. And there are some other odd things in physics. There's a peculiar kind of system called the neutral chaos system, if I recall, which has got some kind of T violation. So there have been a few oddballs, a few oddities in physics, long recognised as having an arrow of time. But chaotic systems, yes, and they're much more ordinary, really. I mean, there's sort of everyday stuff that's been involved in this arrow of time. The problem is, we tend to, as you say, we tend to become a special case of classical systems. And that is because we're still thinking about them in Newtonian terms. And therefore, we miss the mystery. We miss what's so interesting. We need to look at what the behaviour of extended matter as it's processed through these systems. And then I think what's different about them becomes clearer. So rather than thinking of them as classical systems which are odd because we can't calculate, I think we have a different kind of metaphysics here. And in fact, a very common kind of metaphysics is probably in nature, but one that we've not been looking at for a long time because we've been filtering everything through the two-body case.
My question concerns the continuous nature of time and how important that is here. So you stressed when discussing the fact that computers can apparently generate the Lorentz attractor, the fact that actually they're using a discretization of time. But there are dynamics I can set up, such as the ones that generate the Sierpinski triangle, will also have an emergent fractal form independent of the starting condition of the point. So I wonder how important do you see the continuity of time being broadly in this picture, and how close is the Sierpinski example to the Lorentz example?
That is a fascinating question, which I've not given any thought to. I must do so. I think it will not be, it may not matter one way or another, provided the final state is not formally reducible to the initial state. I think that's the key thing. But providing the final state is not reducible to the initial state and there's some kind of principal continuity nevertheless, I'm able to handle both the discrete case and the continuous case of time, but not quite sure. I have to think about that a bit more. Thank you.
Is there a question up here? No more questions?
I just ask one final comment. I mentioned earlier, I think, Western philosophy, since the ancient Greeks, and later what we call science, has been dominated by two main metaphors, the machine and the organism. And they shaped our imagination where we look at the world. The third one I didn't mention was the person, and that's the one that's even more neglected. But we may need another conference on that topic.
Thank you very, very much.